Good morning, students. Today I would like to discuss a problem on magnetostatics. It is a very important problem, and let us first see the problem and then the discussions. Here the problem is an infinite wire carrying a current I is bent in the form of a parabola. Find the magnetic field at the focus of the parabola. Take the distance of the focus from the apex as a, small a. So this is problem, and a conductor is bent in the form of a parabola and which is carrying a current I, and we have to calculate magnetic field due to this current at the focus of this parabola. This is problem. An infinite wire, not a finite wire, infinite wire in the form of a parabola. Infinite wire in the form of a parabola which is carrying a current I, and we have to calculate magnetic field at the focus of this parabola due to this current. So this is problem, and let us see first the diagram. Here this is the parabola. This is the infinite parabola, and which is carrying infinite length. The length of this parabola is infinite, and this conductor is in the shape of a parabola, and this conductor carrying a current I, and here S is the focus of this parabola, and this point capital A is the apex of this parabola, and the straight line connecting these 2 points, focus and apex of this parabola, is the axis of this parabola. And here IDL is the current element, and DL is the very small length, which is a differential length, DL, or elementary length, and which is equal to r d theta, where r is the position vector of a point on this parabola with respect to the focus of this parabola, that is S. And here theta is the angle between this position vector and the axis of the parabola, and d theta is the increase of angle, and r d theta, this is the elementary length, and which is equal to dl. So this is the diagram, and we have to calculate magnetic field at point S, which is the focus of this parabola, due to the current I which is flowing through this parabola. So now let us see the solution. This is figure 1. From figure 1 we can say mod of dl vector cross r vector equal to the area of the parallelogram by dl and r. From vector calculus we know that if A and B, the two vectors, if these two vectors indicates two sides of a parallelogram, then mod of A cross B is the area of the parallelogram. From vector calculus we can show it, and that is why if DL and R, these two vectors indicates the side of a parallelogram, then mod of DL cross R is the area of the parallelogram. So we can write mod of DL cross R equal to area of the parallelogram by DL vector and R vector, and which is equal to 2 times the area of the triangle. Here half times R dot, that is R times R d theta, is the area of this triangle, and R is the one side and R d theta is the another side of this triangle, and the area of this triangle is half R times R d theta, and 2 times the area of this triangle is equal to the area of the parallelogram, and which is mod of DL cross R. So this is very important relation in this problem, that mod of DL cross R equal to R square d theta. This is equation 1, and it is a very important relation in this problem, and we use this relation later in this problem to solve this problem. So this is equation 1, mod of DL cross R equal to R square d theta. Now magnetic field at S, due to this current element I dl, we can get from Biot-Savart's law. From Biot-Savart law we can get magnetic field at point S due to this current element I dl, and we can write it. Now magnetic field at S due to current element I dl is given by mod of B vector, which is magnetic field at point S due to the current element I dl, equal to mod of B equal to mu 0 I by 4 pi dl vector cross R vector by R cube. This is equation 2, and from Biot-Savart's law we can write it. This is magnetic field at the focus of the parabola due to this current element, not whole parabola, only due to this current element I dl. This is very elementary length dl. Due to this current element, magnetic field at the focus of the parabola is given by this equation, and which is Biot-Savart law. This is equation 2. Now for the whole parabola, that is total of this parabola, if we want to know the magnetic field due to total of this parabola, then we can write this mod of B equal to mu 0 times I by 4 pi integration 0 to 2 pi d theta by R. This integration 0 to 2 pi, this integration symbol and this limit is due to the whole parabola. Let us see the diagram. The limit of the parameter theta is 0 to 2 pi. If we take the limit of theta, which is, if we take the limit 0 to 2 pi, then this limit covers the whole parabola, because of the angle will be 0 when the position vector coincide with the axis of the parabola, and if this position vector rotates in the anti-clockwise direction, then the angle increases, and at this position, when the position vector coincide with this portion, then theta increased from 0 to pi, that is 0 to 180 degree, and if again it rotates and again coincide with this line, with this portion, then the limit will be 0 to 2 pi, that is 0 to 360 degree. This is the limit of theta, and which covers the whole parabola, whole infinite parabola. And for the whole infinite parabola, we can say the limit of theta is 0 to 2 pi, and that is why we used here the limit 0 to 2 pi and the integration symbol. For the whole parabola, we can write this, and how d theta by r. If we use equation 1 and 2, then we can easily get d theta by r. Let us see here, dl cross r equal to r square d theta, and if we use this in this equation 2, dl cross r, in place of dl cross r, if we write r square d theta, then r square d theta by r cube, which gives us d theta by r. So d theta by r comes from using r square d theta in place of dl cross r, and if we use r square d theta in place of dl cross r, r square d theta, and which gives us d theta by r, and this comes only using equation 1 in equation 2, we get d theta by r, and the integration 0 to 2 pi is due to the whole parabola, which indicates the whole parabola, and the magnetic field B here, this is the magnetic field at point S, and which is the focus of this parabola, and this is the magnetic field. This is the magnetic field due to the whole parabola at the focus of this parabola. So this is very important relation in this problem. Now next, let us see. The equation of a parabola is given by r times 1 minus cos theta equal to 2a, where a is the length between focus and the apex of the parabola, and this is the equation of a parabola in polar coordinate system. It is not in the Cartesian coordinate system. It is the form of the equation of a parabola in polar coordinate system. R times 1 minus cos theta equal to 2a. So from this equation we can easily write r equal to 2a by 1 minus cos theta, and this is equation 4. Now if we use equation 4 in equation 3, then we can replace this r in equation 3 by this term 2a by 1 minus cos theta. So using equation 4 in equation 3, we get mod of b equal to mu 0 I by 4 pi integration 0 to 2 pi 1 minus cos theta by 2a times d theta, and if we use equation 4 in equation 3, then we can easily write this. And next step, we can write mu 0 times I by 4 pi times 1 by 2a, because of 2a is the constant, and that is why we can write outside of this integration, and we can write this mu 0 times I by 4 pi times 1 by 2a integration 0 to 2 pi. Integration 0 to 2 pi 1 minus cos theta d theta, here 1 minus cos theta is the integrand, 1 minus cos theta d theta. And in next step, if we integrate this, then we can easily write this mu 0 I by 4 pi times 1 by 2a times theta minus sin theta, because of integration d theta gives us theta, and integration cos theta d theta gives us sin theta, and this is the limit 0 to 2 pi. And if we simplify this, if we use the limits, upper limit and lower limit, then we can easily get mu 0 times I by 4 pi, since sin 2 pi equal to 0 and sin 0 equal to 0. So this is the magnetic field due to the whole parabola, whole infinite parabola at the focus of this parabola. So magnetic field due to this whole infinite parabola which is carrying a current I, the magnetic field at its focus is mu 0 times I by 4a. So this was the discussion today. So thank you so much for watching this video.